The title is called Latent Tree Analysis. So the first question is, what is Latent Tree Analysis? Well, now if you've got a few events that happen together and again, so that will typically make us think, why that happened. Okay? And sometimes it could be due to a common hidden cause, okay? Or sometimes just could be purely coincidental. So it'll be quite interesting to distinguish between those two cases and try to identify co-occurrences only due to some hidden cause. And it's interesting, but it's very challenging. Okay, so latent tree model is not something you will use to solve this problem, but instead, it solves a related and simpler problem. Okay, that is try to identify co-occurrence that can be statistically explained by using a tree of latent variables. We have a number of applications in clustering, topic detection, and latent drug discovery. So a latent tree model is basically a tree-structured Bayesian network with discrete variables, and where the leaf nodes represent observed variables, and the internal nodes represent something called latent variables, means the variables you do not observe. There are actually variations of the basic latent tree model. So, for example, in this variation, the leaf nodes actually represent one or more continuous variables. Okay. In other variations, you can have internal nodes. You can have internal nodes that are observed. Also, you can have internal nodes continuous, and the whole structure cannot be connected with the fluorescence instead of a tree. But in this talk, I'm going to focus on the basic LTM latent tree model. Latent tree models have some intrinsic identifiability issues. Okay, so you have this rule, you change it to this one or to this one, those will actually give you equivalent models. This implies that the edge orientations are unidentifiable. So basically, we're talking about undirected models. And also, the latent variables cannot have too many states. If you have too many, the model becomes unidentifiable either. Now, to learn a latent tree model from a data set that looks like this, so basically you have to decide everything behind this rectangle, so which include how many latent variables you want to use, and number of possible states for each latent variable, and how do you connect those variables up, and how do you decide the probability distributions. Okay, it's a quite hard problem, but it's doable. In the past, the algorithms for learning latent tree models have been developed under three settings. Okay, in the first setting, you assume that the data actually generated from some unknown tree model, LTM. And what you do is you investigate the properties of those models and then use those properties for learning. For example, it is known that the model structures can be recovered from the something called the tree additivity of information distances, which can be directly from estimated from the data. And then in this setting, you can actually provide some theoretical guarantees to recover this generative model under some conditions. In the second setting, we do not assume that data are generated from a tree model. We just feed the tree model to the data, guided by this BSA score, and we're going to use search or heuristics to determine the model structure. And this setting does not make sense to talk about theoretical guarantee because there's no ground truth to compare to, right? Because there's no ground truth. And the empirical results indicated that you can actually almost always get a better model in this setting. In the first setting, the reason for that is, in real world, most data sets are not generated from tree model. Okay, in other words, so in other words, this assumption is actually not true in the real world. The third setting is actually an extension of the second setting. So here we also care about the model fits, how the model fits the data, but also want to consider the usefulness of the model. So for example, we want to have a hierarchy of variables. So now we have algorithms that can handle data sets with thousands of variables. For example, here I have 10,000. And hundreds of thousands of instances, or even 1 million. So here's 1 million, here's 300,000. Can do that in a single computer in just a few hours. So for the rest of the talk, I'm going to describe several kinds of applications of the literature model. So I'll start with something called the multi-dimensional clustering. Now, the objective of clustering is just to group similar objects into the same cluster and dissimilar objects into different clusters. For example, if I'm going to cluster this set of pictures, obviously I should do this, right? But now, how do I cluster this set of pictures? But single out for a while is actually two ways, right? One is in terms of the style of the drawings. Another one is just in terms of type of objects in the pictures. Always have two ways. So those pictures actually, have two ways to be partitioned, and this is the concept of multi-dimensional clustering. Okay, so in general, I would argue that complex data usually have multiple facets to it, and it can be meaningfully partitioned in multiple ways. Okay, so if you learn some clustering, all your algorithm has been to looking for one partition. Okay, even you have this hierarchical clustering, but it's still one partition. Except if you cast this tree a thinner ground higher, you get big clusters, right? More coarse clusters. If you lower it, gets more fine clusters. But that's just one partition. So the granularity is different. But here, the argument is that we should look for multiple ways to partition data. So the question is, how do we get multiple partition? Well, to get one partition of data, what do we do? Sometimes just use something called the finite mixed model. So in this kind of model, we have one little variable, and that will give you just one partition of data. So then, naturally, to get multiple partition, you would use models with multiple little variables. Okay, that's actually, literature model is just one kind of such model. So latent tree models has been used to analyze this survey data from the Hong Kong anti-corruption agency, the AAAI, and this is actually a model from that analysis. So this little variable, which is actually introduced during data analysis, is obviously about demographic information, right? You have the age, income, education, and second one is really obviously about people's tolerance according towards corruption, because towards corruption in government, tolerance towards corruption in the business, and whether you're willing to report corruption. The link between them actually is meaningful because people from different backgrounds may have different attitudes toward corruption. Right? And this note is actually about the performance of ICAC, whether it is effective, whether it has enough deterrence in corruption, whether it encourages people to report corruption. And this note is about the corruption level in the city, corruption level in the government, corruption level in the business, and whether the reporter, the government who is reporting actually have witnessed corruption. So this is actually a level of corruption. The link between them obviously also makes sense because if a guy thinks that there's so much corruption, and then they would think that ICAS has not done a good job, right? So that structure can make sense. And then if you look at one latent variable, for example, y2 gets 4 states. So this is one way to patch in the data. And you look at the probability parameters, find out that we get this 4 class of people. So this one is the low-income youngsters. And the second one, this one is actually the woman with no or little income. And this one is people with good education and good income. And this one is people with poor education and average income. Interesting thing you find here already is that say education and incomes are correlated. Okay. For Y3, we'll just give us 3 classes of people based on how tolerant they are towards corruption. It can be totally intolerant, or tolerable. One interesting finding here is that now here in this one, this is the class of people who are tough on corruption. And those people actually are equally tough toward corrupting the government and the business. And this kind of people, they kind of more lenient. Okay, they say maybe sometimes it's okay, but those guys, they would say corrupting the business is okay. Okay, but the government, no. Okay, so it's actually quite interesting finding to us. So, and then of course you can check the relationships between different positions. So here basically we find out that among those 4 classes of people, the people who are with a good education and good income actually are the toughest on the corruption. Okay, and then the other extreme is people with poor education and average income. So they are actually most linear. The other one, the youngsters and women actually in between. So by so we say that military analysis indeed have found several its interest structure and also find several interesting ways to patch in the data, and then and also reverse some interesting relationships among the different positions. Okay, so if you can imagine what you can get by if you apply just k-means on this kind of data, you will not be able to recover this kind of structure. Next, I'm going to talk about hierarchical topic detection. So here we're going to represent each word as a binary variable and also represent the document as a binary vector over the vocabulary. From such data, we actually get it more like this. So we have these words on the bottom, and then we have multiple label of latent variables on top. So this top level 1 latent variable captures the occurrences of words. For example, Z14, if you can see here, Z14 actually captures, it just indicates that the words cart, video, driver, those 3 words often occur in different documents. Not always, but mostly occur together. And same goes for Z15. And then the 16 is image, graphics, display. So all those 2 words tend to co-occur. Okay? And those little variables at high level that captures the occurrence of the patterns on this label. For example, this one just say that those 4 patterns are getting to co-occur. And then each little variable actually is a multi-domain classroom, right? Each one partitions the document into 2 clusters. One cluster is interpreted as the topic, another one is interpreted as the background. For example, Z14 gave us this topic, which consists of 12% of the document, and 15 gave us this topic, which consists of 15% of the document. And then variables on high level, they actually capture long-range word occurrences, so they give us more general topics. And topics at the low levels, they capture short-range word occurrences, so they give us more specific topics. So literally, you get this hierarchy. Next I'm going to show you the result we obtained by pretty big data set, the New York Times data set. So this is actually part of a structure, and the model is hierarchical, okay, but starting here is for visualization. This is actually looks cool, but it's actually too small. So we're going to look at small regions in this model. So here in this part, this is the rule nodes. Okay, this is the rule nodes. The topic they give us is economy and stock market, and it has two children, and this is one. Another one is here. And this one just gives us the economy topic. And the other one here gave us the stock market. Okay, so and then this chart again has some children. They give us some other topics like like prices, merger, property market, and the revenue growth and stuff like that. Because it's a hierarchy, right? From here, you have those two, and this to this two in the hierarchical structure. And here, this part of the model is actually about different companies, in different sectors of the economy. And for example, here we got natural gas, oil drilling, exploration. And this one we got medicine, right? Here we got insurance company. Here we get the stores, the shopping malls, right? Retail industry. And here there's a topic about Enron, because Enron is a company that collapsed during the time, and then that time there were not reports about that event. That's why Enron makes a separate topic.
Right. So to summarize this part, basically we have literature model kind of provide us a new overall message for hierarchical topic attaching, and I cannot. I don't have time to discuss how this is different from the more popular LDA-based method. I will say that the difference in several very important ways, and the empirical results, our method significantly outperforms the method.
So next, Latent structure discovery. Well, we have already said that you can find interesting latent structures use latent tree analysis. But next, I'm going to point out some additional links. The first one is the link to deep learning. This is our model is called hierarchical latent tree class model, and this is a deep neural network. If you look at them, it's actually quite similar in the way that they both define distributions over the observed variables, those observed units here, and they both have multiple layers of latent variables. Okay, but of course the differences are also obvious. One is tree structured and is learned from data. And another one is fully connected between layers and then manually specified. So they have kind of two strengths, and it'll be interesting to actually explore some middle ground between those two extremes. So one idea we have is, why don't we just start from data? We learn a HLTM, okay? Then we use this as a scaling of a deep model. Okay? So after that, we'll add some additional links to make this more complex, and hopefully, you can capture more correlations. Then you can fit the data better. Actually, we have done that. So one of my students, Zhang, will have a paper at AAAI this year. We did something called sparse Boltzmann machine, and this table actually compares the space SVM sparse Boltzmann machine with the RVM restricted Boltzmann machine. You can see that in terms of per word perplexity, on the validation and test sets, SVM is actually much better. Okay. The reason is that the SVM can actually learn a property structure from the data. Okay, then it avoids overfitting. Okay, the RBM on the hand is actually fully connected, so it's not an extra redundant parameters that need overfitting. And there's also need to collaborative filtering. When we talk about text data analysis, we said we use literature models to model the co-occurrences of words. Okay, but in this context, you can use literature models to model co-purchase of items. Right? There's one customer bought several items together. Right? That's actually the fundamental thing in collaborative filtering. Okay, I don't say that's being properly modeled in matrix factorization. But use this one. Maybe you can explicitly model that kind of correlation, and then you can use that. Maybe have a new way of doing collaborative filtering. Of course, you can actually use literature models to also model co-occurrences of symptoms among patient data. You collect data from a lot of patients. You see which symptoms co-occur, right? And back in 2008, we have done analyzed the data set from traditional Chinese medicine. So this is a model. Turns out, those latent variables in the model match the corresponding concepts very well. Okay, so basically, this is quite interesting because the TCM concepts were introduced 2,000 years ago, some say. Okay, of course, they're based on experience. Okay, the experience is basically data, right? Data. So then, what we have done is we have from data, use the computer, we actually restruct the same concepts that is mentioned by Chinese medicine classics. So
also, it's actually very important because these concepts are kind of vague and also very elusive. Okay, you cannot just say what it means. But I will just show that
it's labels people use to label terms. People use to label some patterns they observe. Okay, so go beyond the terms and think about the pattern. Okay,
and also they correspond to software classification, which we can identify from data. So I think it's very important.
That's a message. I think this message is quite important to get the appropriate appreciation of GCM. And recently, people also have used literature model to analyze co-expressions of genes. And then the thing that they say that this kind of analysis is helpful in reconstructing the transcriptional regulatory networks, which is a kind of obvious important topic. Finally, two kind of more traditional applications. Literature model, you look at this one, it actually has two very attractive properties. Okay, this is a property that was mentioned by Pearl. He says that this kind of model is actually very simple to work with because it's tree structure, right? And at the same time, it actually can represent very complex relationships among the observed variables. Okay, you might not have a latent variable, and the relationship among the observed variables can be very complex. And then quite some people, including some of my students, have make use of taking advantage to properties to build something called tractable prediction models for a variety of applications. So that's one direction of application. Another one is go back to social science and some other related science. In social science, people they do this a lot. Okay, they have to perform unit-dimensional clustering on category data. They want to just get one partition. They don't want multiple partitions, just one partition. Okay. The way to do that is they use something called the latent class model. So latent class model is just a latent model with one latent variable, or just kind of standard mixture model, except with discrete attributes. The problem with latent class model is that you have this very strong independence assumption called the local independence assumption. Like this, given this one, all those attributes are independent. Okay, so people have been talking about how do you relax this assumption, and this literature model actually provides a lateral framework where you can relax this assumption. And this actually how we studied this work about 50 years ago. So to summarize, linear model can be used to model co-occurrences of words in documents, can be used to model co-occurrences of sentence on applications, can be used to model co-purchase patterns of items in the transaction data, can be used to model co-expression of genes and correlations among answers to several survey questions. And it can be applied to multi-domain clustering, hierarchical detection, data and structure discovery, tractable models, and then also relax the local inference assumption of Latent classical. And I think that's the end of my talk. Actually, I want to